So via acceleration on the space-time diagram, we've been exploring the effects of an actual gravitational field. But of course, there's no gravitational field in our space-time, and these paths that we've been exploring where we're accelerating like this create this event horizon, right? So that there's this 45-degree line that you approach on the space-time diagram, and that's the event horizon. But let's say that at, say, this location here, instead of continuing to accelerate, you now stop accelerating, and you're going at some speed. So you have some tilt here, and so you're now in an inertial frame where your time axis looks like that, and your space axis looks like that. And so you're an X bar, T bar observer. And when you do that, then what were previously events behind some event horizon. So here's a world line, here's a path through space-time of some observer. And these were the events. So we can single out a few events. Let's make a few more here. These were when you were accelerating. If you continue to accelerate, all of these events were hidden behind an event horizon, because the 45-degree line means that you can never communicate. You never have access to these events. But notice that once you stop accelerating, you now follow the green path. These events are all accessible to you, so and so on. Basically, what you've done is to transform away this gravitational field via the principle of equivalence. Right? You stopped accelerating, so you're no longer subject to this gravitational field, and the event horizon has disappeared. So by eliminating the gravitational field, so maybe we should say you changed your perspective. You jumped into a frame that is no longer accelerating, and got rid of this gravitational field, and with it the event horizon. We sort of created a gravitational field, a fictitious gravitational field, by accelerating. But this is not something that you can't eliminate a real gravitational field entirely the way we did here with the fictitious gravitational field. And we can see this by imagining that a real gravitational field is not like the one that we've been exploring in terms of a constant acceleration g downward everywhere, whereby if you're in the elevator that's in free fall and you release your apples, they will just sit there with respect to you as if there were no forces, as if you were in free space and no forces acting on the objects, on the two apples or on you. A real gravitational field is such that if you did this and you released the apples, they wouldn't just sit there with respect to you. Over time, you would notice, so as you're approaching the Earth, you would notice that the apples are actually moving inwards. So there is a force. They're moving inwards because of the way the gravitational field is. The Earth is actually round, and it's not a flat, infinite plane the way we had it before. So what we really can say is that a real gravitational field can be transformed away only to a first approximation, but that you will eventually see the existence of the real gravitational field. And so we'll want to get a sense of this mathematically. We'll say that locally we can transform the gravitational field away, but that overall the gravitational field will show its effects.